23 on my scale, and they weighed 154 pounds, so I put a dot there for 23, 154. And then I put a dot here for 22, 154. I put a dot here for somebody who was 24 and weighed 210 pounds. I put a dot here for somebody who was 27 and weighed 216 pounds.
Right.
So I'm just putting dots.
But that line, what is that? Why is that significant? Is that just saying that?
The line
is,
is, well, we're going to try to get the equation that gives us that line. Now, that line will not lie. So what we want to do is we want to minimize the distance between these dots above and the dots below. Well, sometimes we get a good line, sometimes we don't. Okay? But we don't know that until we get a line. So when I look at this, I have to fill out all these different columns. So that's where you guys were supposed to have done this already. And how do I get the mean of the duck weight? I take this, okay, so there's my formula. Now, I can actually do this, and I do this sometimes where I have these numbers, and I just write the formulas. What's the formula for this number? A minus AW, W minus W. It says to take what, 2 boxes and multiply them.
Oh yeah, the D26.
Okay, it says I'm going to take D and multiply it by
G26.
G. And I need to do that for all 20 pieces of data.
That's so cool. That is way cool. We were wasting our time.
Oh my God.
And I just did it. And I was nice because I set this up to give you all the sums in the nice little yellow boxes, right?
Right.
So when I look at this, A minus AW, so there's my sum, which is 429.65, yes? So when I do this, I get 429, what was that?
29.65.
65? And then I divide it by the sum of A minus A squared, which is this column here, column E. So I'm going to take this number, which is 376.8.
Your H column is different than mine though.
Yeah, your each column is different.
How come?
Wait, what?
We got 6,201.
What happened? Yeah, that's very different.
Oh, because I'm not looking, here's my H. I didn't do H, that's just A and W.
Oh.
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 No. No, your
Yeah.
W2, your W minus
W.
your W mean
Yeah,
squared is different from ours.
Yeah.
So we took the G26 and we squared.
you took G and squared it.
Oh, yeah, we took the G26 and then we squared it.
Okay,
And I got a different answer than you have.
You
I
got-
have 1092.30,
G26.
right? Isn't that right? See? This one, I picked, I did the equal sign and chose this one and then I squared it, which gave me this and then I brought it out.
Because you didn't do this form, this one right.
I did it? Should I
No, you took C26. Oh, let me check something. I know what I haven't done yet.
The dollar sign?
No,
What?
You didn't find the mean. You were diving
I subtracted the mean, but I have not calculated the mean yet, have I?
For the weight.
You made us all think we're doing it wrong.
So I have to go back and divide the sum
But
by
we're good. We're good.
n.
Okay.
There we
which gives me
go.
187, and now it's
That's
just
right.
fixed all of them.
That's,
Alright,
that's
cool, you
exactly,
gave us a
yeah.
hard time.
Okay. See, this is where, see, I wrote the formulas before I actually calculated the mean. But see, you saw how I could tell it to just divide by the mean,
Yeah,
or subtract the mean from everything. I just didn't have the mean in there, so if there's nothing in that box, it counts it as zero. Okay? So now I can actually do this correct, where, actually, it wouldn't have affected that number at all,
you wouldn't?
I don't think.
So
No, I
the
think
A
it
minus
did.
A, that's 376.8. 376.8. No?
So let me see here.
No, it'll be 152.0.
So
Over number.
it's 429.65 because it's this column times this column,
Uh-huh. Yeah,
D26. So it's this one times this one,
that's 429.65 divided by,
which is 429.65.
and then we divide it by what, the 376.8?
429.65. And then we divide it by
The 376.8
A,
minus the A mean squared, right?
okay, minus this column, which is 376.8. So that's all that formula does. Now I'm going to use Excel to calculate that. So I'm going to come down here and I'm going to say my B is equal to, and basically to do this, I'm going to say equals 429 divided by 376. I just clicked on the two boxes,
1.1.
which gives me 1.14. So what does that 1.14 mean?
Yeah, what does that mean?
It means for every 1 centimeter increase in, or not centimeter increase, because what are my two variables here? Age and weight. So it says, for every 1 year of age, I add 1.14 pounds.
That's a lot of pounds.
So it says, basically it says, for every year that you get older, you're going to weigh about 1.14 pounds according to this model. Now, in this particular, now, how do I calculate the A, which would be the A? So the A, we get by taking, and see, I always have to think about doing this. I always have to go back to here to get this. Y cap equals A plus BX. We want the A. So that means I have to take Y and subtract BX, which will give me A. I just rewrote the formula. Now, the only thing is that to use this formula to calculate the A, we have to have some value to use for Y and X. And the values that we use are the means. Yeah, the means. And the B we just calculated, right? See, the B is this value right here.
Okay. So now the formula is A,
It's Y cap, or Y bar, minus B times X bar.
B times X bar.
So that means I have to go back to my sheet, and here is my Y bar, 187.3.
Wait, what was the Y bar? 187. Why is that a Y bar? The W?
The weight. In this particular case, it's weight. So if I wanted to change this, it's the weight bar minus the age bar, the mean of the age. The mean of the weight's minus B times the mean of the age.
So the y bar is the dependent variable.
Correct.
And
Minus 1.14 times X bar, which was 27.6.
So you basically just put it in, like the number.
And that will give me my A.
was A. So 187.3 minus 1.
So again, now I'm going to calculate my, just up one row. I'm going to calculate my B, or my A, equals, take these two boxes and justify them this direction.
Do we just go straight across or do we have to do PEMDAS?
What do you mean?
Like, do we do 187.3?
Okay, so I'm going to take my 187.3 minus my 27.6 times my B, which we just calculated,
Oh,
right above it, which gives me 155. Theoretically, that is my y-intercept, and basically what this is saying is when you're 0 years old, you weigh 155 pounds. Which is a bunch of malarkey. Remember I said sometimes the y-intercept does not make sense? I can't take this data for 23-year-olds to whatever, 33, 35-year-olds? What's my lowest age, my minimum? So see, this formula is only good for people once they get to a certain age, It can't really predict back to when you were born because we all know that babies don't weigh 155 pounds. Or else most of you in here, everybody but me and Bronson would probably be in terrible shape if babies weighed 155 pounds when they were born.
Got it. Got it.
Yeah, so we know, so see, in this particular case, the y-intercept really doesn't have real meaning. In other cases, the 0 point can have absolute meaning. But in this particular example, the y-intercept has no real meaning. Not a meaning that we can put a definite comment to. So now we got the equation. The estimated weight is equal to, what was that, 155.83 minus, or plus, what was that? Huh? 1.14 A. So that is what we call our equation. That is the linear regression equation. Which theoretically says, we could take somebody, we could predict, if we had somebody who was 50 years old, we could take this equation and predict a weight for that person. By saying, well, their estimated weight would be 155.83 pounds plus 1.14 times 50. So we use the equation based on some data so that we can predict things that we don't actually have data points for. So see, we could take this equation and weigh some, what's your age, and get a predicted weight. Now, some equations are good, some equations are crap. So we want to know how good is this model? And that's where R comes in. For every equation, we calculate a thing called R. and R is called the correlation coefficient. Now, what is correlation? What does it mean to be correlated?
Connected.
Huh? They're somehow connected, but correlation does not mean causation. Okay? Two things can be correlated, but one has no cause to the other. That was the big argument for years about cigarette smoking. Everybody agreed there was a correlation between smoking cigarettes and cancer rates. But they kept saying, well, we don't know if it's the cigarettes that are causing the cancer, because there were people who never smoked who got cancer. And there were people who smoked like a chimney and never got cancer. So smoking cigarettes, like my Uncle Ham lived to be 97 years old. Probably smoked a pack of cigarettes a day. Kept a bottle of, let me see, Uncle Ham. Grandpa Locke was Echo Springs. I can't remember. I think he might have been Jameson. I remember most of my uncles by the bourbon that they drank. Okay? He slept with a bottle of bourbon next to his bed, and at night before he went to sleep, he'd pour himself a shot of bourbon and go to bed. And first thing he did in the morning when he woke up is pour a shot of bourbon and wait before he got out of bed. Sometimes he took a couple of shots during the day, but shot at bedtime, woke up. He rolled his own cigarettes when I was 5 years old. Me and all my cousins learned how to roll cigarettes because he rolled all his own cigarettes using bugler papers. So me and my cousins all knew how to hand roll cigarettes. But he smoked cigarettes. But see, he rolled his own cigarettes, grew his own tobacco. No chemicals in it. So see, that's what they were arguing. Sometimes they argue it's the chemical additives that they add to cigarettes that cause the cancer, not so much the tobacco. I don't know.
Right.
That's been an argument all along. But there was a strong correlation. It took a long time before they could prove a causation. So this is all we're doing here is saying that these two variables are correlated. And now we want to know how well they are correlated, or how much one variable predicts the other. And that's where we calculate what we call the correlation coefficient, which we use the letter R for. So whenever you see R, we're talking about a correlation coefficient. And then we will square R, and we call this the coefficient, I hope I got this the right way, of determination, or determinant. There's about a 20% chance I got these backwards. So if you look in the book and it says I'm wrong, it just says that I flip-flopped them. I'm terrible at flip-flopping things. Huh? That's why you write things down. That's why you write these things down on a index card. Because if I had to do this in real life and I wasn't 100% sure of it, I'd go look it up.
Yeah.
I'm like 80 or 90% sure I got these right today.
Right.
Okay. Now, the formula for this looks really, really scary.
Like everything else we went through already.
Yeah.
Okay? Here's the formula for that. Oh, shit.
Wow.
It says to take the n, which is the count, times the sum of the x times y column. Well, if you go back to this, do I have an a times w column?
Yeah.
No.
Oh, 8 times W. No.
I don't have an a times w column, so I have to calculate an AW column. Well, where do I find my A value?
B 20.
B times this. And what does this big sigma tell me to do? Sum that column up. So I just summed that column up. So now when I'm looking at this, okay,
Was it 8198, 103819
okay. So I'm going to take this and slide it over here for a second. And then I'm going to come over here and open a new page. So my R is N times the summation of XY minus the summation of X times the summation of Y. Again, I'm going to normally use Excel to do this, okay? So if I'm looking at this, so I'm going to hide some things in the middle so I can see my columns. So I'm just going to hide my data momentarily. Okay. So see, I've got my column heading, and here I've got my sums. I don't need to see all that data in between. So here's my X times Y summed up. So that says take this number, 103,819.25, and subtract the summation of X, which in this case is A, which is 552, times the summation of W, which is 3746.
What did you get that 103,819.2?
Right here.
Yeah, how did you get that?
I took A times W,
Yeah,
and then I added up that column.
that's the sums of A and W.
That's A times W, that's the sum of the products of AW.
Go to like this. Times when you go straight down to the question.
I multiplied the number that was in column B times the number that was in column C. That's where AW comes from. Just says take the independent variable times the dependent variable for all 20 cases, and then add up those 20 numbers. And I forgot the N, which is 20. So I have to take 20 times that 103, because see, the formula says take 20 times that sum minus this times this. So now when I do that, I will normally do this, and if I'm doing this on Excel, I do it in 5 steps. This is my numerator. Which just says take my N, which is 20, it's in box B47, and I multiply it by the number that's in L, the sum of L. and then I subtract the sum of B times the sum of W. And there's my numerator, 8,593. See, so even though this looks intimidating, it's 1, 2, 3, 4 numbers. So I multiply two numbers and subtract the product of another two numbers. I'm not looking at each data point, I'm just looking at the sums. Now the bottom gets a little more difficult because I need to take a square root. And then I've got two parts.
Was it brackets or parentheses?
Well, either one. And here I normally use square brackets because I use parentheses around the summations. So I'm going to take my n again, which is what?
Count.
The count, which in this particular case is
20.
20. And I'm going to multiply it times the summation of x squared, which in this case would be which variable?
A.
A. And then I'm going to subtract the summation of A squared. So now see, this is going to be my independent variable denominator. Okay? So in this particular case, I'm going to take equals. Where do I find my n? Which is in what box?
Number.
It's either in A47 or C47. Doesn't really matter which one of the two counts I use. They're both going to be the same. And I'm going to multiply that by the summation of A squared. And A squared is in what column?
H.
In my particular one, it's in column M. And all that means is I took all the values in column A and squared them, and then I added them up. So if I'm writing this out up here, I've got the square root of 20 times the summation of A squared, which in this case is 15, 6, 12. And then I'm going to subtract the summation of x, which is what? In this particular case, my x is what variable? A. So the summation of A is what? 552 squared. So that's half of my denominator. So if I want to write that, see, so I'm going to take, well, the 15, 6, 12 was in box M, was the sum of my M column. So, and I'm going to subtract the sum of my A column squared. Okay? And then I'm going to do the same thing with the y. So I'm going to take 20 times my, my y is what variable in this case? W. So I'm going to take my w squared, which is in column N, that. So I've got to open this back up and unhide those.
Can you make the top one smaller so you can see the whole thing?
Can I make the top one, what do you mean, the top
The
box?
whole-
No, I can't, not be able to write.
Oh,
I mean, if I make it smaller, I can't write that small, that's about the smallest I can write. It's just a long formula and you gotta be able to, so basically, the formula was right there. And I have to be able to pick those numbers up, and they're big numbers, so it's not going to be easy to write it out small. Okay? I mean, it's hard to do it. Okay? Which is why, when I do it on Excel, I do it in pieces. Okay? So, how am I going to get this value? I'm gonna square W. Where do I find W? In column C. So I'm going to take column C and square it. And I've got to do that for all 20.
55 squared? How come you have 55 squared and not 552 squared?
Huh?
I think you forgot two.
Oh, the 20 times 15612 minus 552 squared? Is that-
Minus 50,
the last
1,500,
the last one.
15,612 minus 550.
2, right?
2 squared.
552 squared.
You forgot two.
When I was writing it, I just let the 2 become,
Right.
which is why I normally don't do these by hand, and I just click on the boxes where those numbers reside.
Yeah.
Because then I don't have to worry about making a typo. Because that's 9 times out of 10, when I make a mistake, it's because I make a typo.
Yeah.
Everything wrong.
And then everything's wrong. So there's my 20. So now I can get W squared. So I'm just gonna add that column up, and that gives me what? 707, 827? 707, 827.6.
Which one is this? What is that? What is that?
W squared.
W squared?
The
is
sum of W squared.
The sum of W squared.
The sum of W squared. And then I'm going to subtract the sum of W squared.
Where's the formula? I didn't get to finish writing that.
It's
Wow.
it's in the Word document in resources.
It's the same thing as the X.
In Word.
Okay.
So this would be 3746 squared. So now I'm going to do this, and I'm going to calculate the dependent variable in the denominator.
Under the regression sets? What was it under?
It's a Word document that says regression something or another.
Linear.
Linear regression.
Linear regression. So let's write this one back on.
Yeah. Oh, it's so big, that's the denominator.
So there's that part. So now what I'm doing is this piece right here. Again, I just have to find that. So I have, how many different numbers are here? I got 20 times something minus something squared. So I'm going to come in here and I'm going to say down here, I'm going to say equals to 20, which is in box C47 or 8B47, doesn't matter which one I use, times the summation of W squared, which is this number here in N46, minus the number that's in C46 squared. And then I want the product of those two numbers.
So smart for him to do concept farming and.
But see, if you can go, if you did that worksheet where you could grab those sums, you're just grabbing those numbers out of that box.
Yeah.
Remember, you got those, all those sums on that sheet that I gave you to do on Tuesday. So you're just working with all those sums. You're just grabbing those different sums. And then I want the product of those two numbers.
You times it, right?
So I'm going to take this number, the independent variable denominator, times the dependent variable, and that's going to give me some great big number. And I have one more step I need to do with that.
You square it, right?
Not square it, I need to take the square root. Square root and squaring, they're related, but they're not the same. How do I get the square root? SQRT.
Oh, on the Excel, does it on the calculator? You just push the square root?
So I get a number that's what, 30,573. So that is this is the actual denominator. So to get my R, I'm going to take my numerator, which is what? 8593, and divide it by my denominator, which is 30573.503. So that means I'm going to take this number divided by this number. And my R is 0.28. So how do I interpret this 0.28? Basically what that says is 28% of the dependent variable weight is predicted by the independent variable age, which means that this is almost next to worthless model. The linear regression in here I would never use, because that R is just way too small. We want an R that is somewhere, the closer to 1 or -1 that the R is, the better we are. And it should always be between -1 and 1. So if you ever get this and it's a whole number, you've done something a little bit wrong. But you just need to be able to grab these different pieces. So basically what I would say is the weight would be terrible. So basically what you're going to do is for each one of these variables, you're going to have to do this what? 1, 2, 3, 4, 5, 6. You're going to have to do this 6 times.
Oh, it's a times what?
You're going to have to do this 6 times. You're going to have to create 6 equations, and you're going to have to calculate the R for all 6 equations.
Okay.
This thing right now.
Okay.
Yeah.
Can I go back
Now.
to your answer? Can you go back to your answer so I can see your answer?
I think I have it. It's in the back.
I'm getting it.
If two of us get it, the rest of us will get it.
Now,
Okay.
all that said and done, that's the equation, that's the variable that they give you in the book.
Yeah, now, this thing right now.
Yes.
Yeah.
There is an easier equation to do.
It's novel.
But at least I forget it.
There is a easier equation to do.
Well, then why are we doing this?
Okay. But I mean, basically, this is the formula they give you. This is why I say if you just go out to the internet and Google something,
Yeah,
there's a bunch of different formulas for it.
I see. Uh-huh.
But there's a different formula for this that gives you the same answer.
All the pages, you will print that automatically.
And the formula for that is to take whatever you calculated for your B and multiply it by the standard deviation of X divided by the standard deviation of Y. Which in this case, we just said 1.14 was our B. And if we go back to our data, well, what's my formula for standard deviation?
We already have the standard deviation, right?
The standard deviation for X is the summation of, well, in this
The
case,
variance.
what is my variable? What's
The
X?
variance. Well,
X is my age.
age.
So I want to take my A minus A bar
Uh-huh.
squared and divide it by N minus 1.
Well, that would be the variance.
That would be the variance.
Okay.
And then if I take the square root of that,
Oh, right. Correct.
I get the standard deviation.
Right, okay. Okay.
So if I'm doing this, we have the, again, we go back, but you still need the columns, right? So I still need A minus, I still need my column E.
Uh-huh.
And I need the sum of column E, which is what? 376.8?
Divided by 19.
376.8 divided by 19.
And then square.
And then I take the square root of that.
Uh-huh.
So,
Which is the 4.45, right?
right. So see, if I want to get my standard deviation, I'm going to take the square root, I'm going to take the square root of 376.8 divided by 19,
Okay.
which is 4.45.
Or, tap it on the cell to figure it
Uh-huh.
out.
And then I'm going to do the same thing for my
Second.
standard deviation of weight, which is the square root of the summation of W minus W bar squared divided by N minus 1, which is still the square root. My denominator is still 19, but W minus W bar is in, squared, is in column H.
H46.
So it's 6201.825. So I get that by saying take this sum divided by 19.
Oh, I don't have.
And I didn't take the square root of it. If something seems to be real too big, so see, I didn't actually take the square root.
Oh, yeah, that's what I typed in.
If your number seems way too big, that's normally what happens, is you forget to take the square root of it. Most of the time I'd calculate and I'd have the variance in there and then I just take the square root of
I
the
was typing in
variance.
standard deviation, but it's square root of that number. It's not
Right.
standard deviation. Or you can just type in standard deviation and just highlight the weights.
Yes. So then to calculate my R, I'm going to take my standard deviation of X, which is 4.45, divided by 18.07. So the alternative method for calculating your R is to take your B, which is in box H47, and multiply it by your standard deviation of X divided by the standard deviation of Y, which in this case is W, and you see that you get the exact same answer.
Could you click R again?
So I'm taking
R.
B
Where'd it go?
H50?
times the standard deviation.
Is that formula right there where I took B, which is this number right here,
Ah,
Right.
times this number divided by,
And you put it in
This
parentheses,
number.
right?
I do put it in parentheses, because I always doubt that, I always have a little bit of fear.
It didn't work when I did it.
Yeah, it should work, but
I had to put
sometimes,
the times. It didn't work when I just put the parentheses. I had to put the actual times.
yes, you do have to put the asterisk in to tell it that it's multiplying.
Okay,
Okay.
got that.
Okay. Start.
So see, there's the alternative formula. It's still on that same sheet with all the linear regression. So basically what you're gonna do is you're gonna make a linear regression, you're gonna make a regression line for each of the variables we have not done. Which basically means everything that you did in that sheet and got all the sums, you should have everything you need. You shouldn't need those other, if you use this formula,
What is B?
if you use this, B is that one right there. That's the slope that we calculated for the line. B is the slope that we calculated for the regression line. So you gotta find the regression line before you can find R. Okay? So once you found this, so this is your B, this is your A, and that gives you your regression equation. Y equals A plus BX. So see, you're gonna make this equation for each of the variables. So that means you gotta do it 6 times. And for each one of these, you gotta do this 6 times to get the B for each of your independent variables. And then you're gonna have to do this to get your A or your y-intercept for each of the equations for your independent variables. And then you're going to calculate your R.
Wow.
You gonna look for a bar?
Look for the bar.
Huh?
Look for the bar.
You look for a bar.
Well, what would y bar be?
No,
No,
the
bar.
bar.
B-A-R.
B-A-R.
Bar.
Okay, I'm terrible at catching things like that, yeah. And then you're going to calculate the R, which I'm going to use this formula most often. This is the formula they give you in the book. I can walk through it. If I try to type this in one formula, I always get it wrong. Remember I said I do it in 5 pieces? So see, the first part I did was the numerator, then I did the independent variable, then I did the dependent variable, then I multiplied those 2 answers, and then I took the square root of that answer.
Yeah.
And that gave me the denominator, which I then took and divided the first thing I calculated by that denominator. So it takes me what? 1, 2, 3. Takes me 4 steps to get the denominator. 1 step to get the numerator, 4 steps to get the denominator, and then I divide those two numbers to get my R. But this is just basically the same as that.
So which formula will be on the midterm?
The
Probably
last
that.
one, right? Not
Which
the,
formula will be on the midterm? Let me see.
The easier one. yeah.
What formula will be on your 3x5 sheet that you bring in to take your test?
That one.
The bigger one?
No, whichever one you
Oh.
wanna write
No,
down.
whatever we want to write.
Whichever one you
Then-
happen to
then
write
take-
down,
Yeah.
whichever one you happen to write down on your 3x5 index card is the one that you will use, because I won't give you the formula.
Okay. Yeah, that's what I'm trying to say.
Or I might give you this formula,
But then we'll
but
just.
remember you're allowed to have your 3x5 index card with your handwritten formulas, right?
Right.
So
Front
if you
and
write
back.
that, then you can use that, right?
No, just checking because if you ask, use the big formula, like, oh my goodness.
No, I'm never gonna tell you what formula to use. I'm gonna say calculate R. I'm not even gonna have either one of these formulas.
Calculate the R. in
I'm gonna
R.
say, give me the regression equation, so I expect you to give me this, which means you have to calculate the A and the B, and write the equation, W cap equals whatever, and then I'm gonna say, what's the R? So you're going to report to me what the R is.
right, we use that formula for R.
I don't care which formula you
No, but
use.
we're gonna use that formula for R.
Okay, so that's basically where you're going to boil down to. So you get, that's why even people who do a lot of statistics, we know where to go look for the formulas. I don't have these things memorized. There's too damn many of them. Okay, where do I have the X and the Y? Where do I have the X? Yeah, the formulas are too big and complicated physicists, when they have to do a lot of things, they don't have all the formulas for all the propulsion and all that.
Unless they Sheldon.
Memorized. No, even Sheldon probably goes looks them up. Well, he has an idyllic memory, and there are some people who have an idyllic memory that can get away with it. Most people do not. Okay? And then what you're going to do is, the bigger the R, and your R can either come out to be positive or negative. But it should always be between -1 and 1. It will always be a decimal. R should always be a decimal.
R is always a decimal between 1 or negative.
Between 1 and -1. If R is positive, it means that your slope is
We're not.
positive. If your R is negative, it means your slope is negative.
Between 1 and what?
-1.
1.
It's actually between -1 and 1. There is a difference between 1 and -1 and -1 and 1. The difference being, the difference between the distance from Guam to Hawaii is that you start in the west and go east. It's a very short distance from Guam to Hawaii. But if you start in Hawaii and you go west to east and you have to go all the way around the globe, it's a heck of a lot longer. So there is a difference between 1 and -1 and -1 and 1. Because sometimes we live in things that are circular. And it's from going around the clock this way or which way you're going.
And the
So-
better R is closer to +1.
No, doesn't matter.
Doesn't matter.
Doesn't matter. If it's a negative, what that means is your independent variable is just saying, as your independent variable decreases by 1, your dependent variable, or as your, the independent variable increases by one,
It
your
looks-
your dependent variable goes down instead of up.
No, I don't get more, there's no more in
So if I calculated it, and I got an R of 0.90, or an R of negative 0.90, which would be a better R?
That one, the
The
top.
positive.
No, those are both exactly the same. Well, they both say that 90%
Oh, yeah.
of the variation in your independent variable is explained by the variation in your independent variable.
Okay, that was just like, what? What? If they both say that the independent variable is what? That 90% of the variation of the dependent. 90% of the variation of the dependent. Is what variation? Is the
90% of the variation of the dependent variable is explained by,
is explained by.
did I not put explained
No,
in
it
there?
just
No, it's
doesn't
on the
go
other
out.
side. It's more
Whoops.
expanded.
The,
Is explained by the variation of the independent variable.
of the independent.
More or less.
Okay.
So it's just saying that a lot of, so that's all that is. And if it was a negative 90, it's still saying 90%, but it's just saying instead of the slope going up, the slope is going down, but it's still 90%.
And it's still dependent.
Yeah. That's what your R is explaining, is the variation between the independent and dependent variable. So the bigger, the closer R is to 1, the better the equation is. So remember, what was the first part I told you to do? Make all the scattergrams, look at it, and decide which is the best and which is the worst based on visual inspection. So there is no right or wrong answer. It's based on your visual inspection and your interpretation of looking at the scattergram.
But they're not near one.
Huh?
They're not near one.
Well, when you draw your scattergram and look at the picture,
Yeah, I'm looking at it, yeah.
yeah, you have no numbers to do it. So see, what you're gonna do is you're gonna create all 7 scattergrams. And then you're going to choose which variable you think does the best at predicting the weight based on the independent variable. So does age, height, chest circumference, knee circumference, forearm circumference, bicep circumference, knee circumference. Which one gives you the best prediction of weight? I want you to do that by looking at the scattergrams first.
Yeah.
There is no right or wrong answer.
Yeah.
I want you to look at it and say, I think that this one is the best because,
Because half are.
and this one is the worst, and we can pretty much guess that age is going to be the worst. Because age has really nothing to do with weight, okay? Height has much more to do with weight, so we would expect H to be a better predictor. We would expect height to be because we'd expect somebody who's 6 foot to weigh more than somebody who's 4 foot.
Okay, so the amount that are above the line or below the line have nothing to do with anything?
Maybe. See, that's what you gotta look at it
Because
visually.
the age looks like it's pretty close. You
Yeah,
know, I mean, but more up on the top and more some of them.
but see, that's what you're gonna have to sort of look at, okay?
How straight across are they going? Above
How,
the line?
what the different graphs look like. So I want you to create, I did 2 scattergrams. I did age and height, right? So you're going to do the other 5. And then you're visually going to inspect those scattergrams. And just make a prediction based on what your eye tells you. Then you're going to go back and create all 7, and well, all 6, because we've already created the regression equation for age. So you're going to do that for all the other variables. And then you're going to calculate the R for each equation. And then you're going to say, based on the R, which is the best and which is the worst. So once you get your R, you're going to come back. And then I'm going to say, did your visual inspection give you the same answer as your actually calculated R? And I don't care if they're different. But see, what you're going to start to do is look at things and sit there and say, I can't just always look at data and say this is best.
But when I see an R that's saying it's like 0.8 or 0.9, something closer to 1, then I know, okay, that one.
0.8 would be better than
one.
0.75.
Right, that would be the better one. And then I would say, okay,
And-
visually, did I get
And
that?
-8 would be better than 0.75.
Right.
Doesn't matter which way, just as the closer to 1 or the closer to -1.
Okay. Okay.
Doesn't matter. If it's 1, it just says that your slope is going like this and there's a positive correlation. If it's negative, it says that you have a
Negative.
negative correlation, which says as one variable increases, the other one decreases.
Is that why, like, for like psychology and FEMR, they have those charts that talk about correlations and all that?
Yes,
So that's how they got their.
yes. When they start talking about a
Yeah,
correlation
correlation
factor
between
of
Yeah.
0.85 or a correlate, that's what
Has a
they,
stronger correlation.
that's what they're talking about, a strong correlation. The correlation is closer to 1. So see, they do some regression analysis to come up with a model, and then they calculate the R to see how well their model predicts reality. And that's what they are, exactly what they're talking about with the correlation, how strong the correlation is. Is there a strong correlation or a weak correlation? So yes, so when you're in FAMR and you're looking at, what is it, the DSM-2R, whatever it is, that big fat book,
Yeah, and it's like.
and they start talking about all the different psychological neurosis or whatever. I gotta be careful, I don't want to offend anyone. But yes, medical field does that. Economics does that. They create all sorts of models. Basically, when you look at the hurricane prediction models, they're all based off of the same sort of stuff. They do these correlations, and then they calculate and say how well they think that model correlates to what they're doing. And all the different models will have a different R value. And sometimes I can have 5 or 6 different models, and the correlations are fairly close, and that's what they start looking at. So when you start looking at like the hurricane prediction maps, they're all using regression analysis. It's normally not linear, because they don't go in a straight line. But they use that, and then they actually calculate an R for how well it is. The other thing that they do with those correlations is they normally involve more than one independent variable. You can have, the worst I've ever done is I did one model that had 6 independent variables predicting one dependent variable. So it was 7 variables. And basically we developed a model, and then we had to calculate an R for how well each of the variables predicted. So we calculated an R for the overall model, and then we calculated an R for each of the independent variables. So we calculated 8 different R's, 7, I forget what it was.
In the real world.
In a real model, yes. So yes, that's the hardest one I've ever done. In doing different things it was an economic model based on six independent variables predicting one dependent variable. So we came up with a big model. Used a lot of computers. It took, even with a computer, it took 3 weeks to do.
Wow.
Using a computer. Back when I first learned how to do this, what we just did with that regression analysis, with me talking through it, would have taken me a week to do. Even using a computer. Because basically for me to do a computer, basically I still had to use punch cards.
Type it all in.
So you'd have to do a stack of punch cards, and you'd have one card for each set of data. And then you'd have to read those through. And the aspect behind it is, if you're like me, you make a lot of typing errors, so I'd have a stack of 1,500 punch cards. I'd run them through a reader. And then it would take the computer maybe anywhere from 8 to 15 hours to turn it around and give me a readout. If I had 1,500 cards, the first readout normally said there was a typing error, and it would just give me a list of about 100 cards or 200 cards that I made a typing error on.
And you have to
So
find
then
it.
I'd have to go back and get that card, take it out, retype it, put the new one back in, and I'd have to run it again. So normally when I took those, huh? A punch card was a card that was like about this long. It had 36 columns and 8 numbers in each column. And it was all binary code. And so like when you typed in a number, you had to type and it punched out holes, and then the computer just read whether or not those holes were open or closed.
But I
Thank
saw
God we're
movies
the
on
modern
it.
world.
So you would do
That's
that.
what I'm thinking. Yeah,
And
so
you
he
would
was
run that-
thinking, he's like, and you guys complain about
Yeah.
this.
Yeah, and you're sitting there running it through, so we'd run it through, so if I had to retype 200 cards, then the next time I only had 20 cards that had typing errors, so it would take me about 4 feeds just to get it through before it had no typing errors. And each time it's going to take me between 8 and 15 hours. So that means,
That's why it took so long.
that's why it took so long, is because each time you'd have to do it, you'd have to wait. But if I had to do 1,500 of these subtractions, where you just saw in Excel, I can just write the formula, drag it down, and I can do 1,500 of them in a matter of about a minute. I can do those 1,500 subtractions. But on punch cards, I'd have to do that for each card, and then I'd have to square that for each card. So each one of those columns would represent a card.
Thank God we live in this world.
So when you sit there and you start complaining about doing this, it was a lot different. And a lot of the things that we do now, we can always do them. It's just that it took so much effort to do it that normally by the time you did it, to create a model to predict something, the event had already happened that you were trying to predict, and you can just look at the results. But now with computers, we can do these calculations almost instantaneously. Stuff that used to take me weeks and weeks to do, I can now do in hours because of Excel.
And we complain.
Yeah, that's what I'm thinking, right? I was like, at least they're not in that age.
I took attendance,
Oh,
I'm pretty sure.
You did?
You did?
You can call our name.
Because you know our faces already, guys.
Actually, no, I didn't.
Oh.
Mine's not even
See?
open. So math 115.
just make sure to forget next week that we're all here. I mean, not next week, but Thursday.
Okay, today is Tuesday the 6th. So let me see, Bronson was here. Imani. Monique.
Did you not